Yeah, hello all. I guess I'm audible. So this is Ruthvik, and in this session, I'm gonna take the PCD for LeetCode Weekly Contest 486. Okay, let's start. Coming to the first question, the name of the question is minimum prefix removal to make the array strictly increasing. Actually, the name itself explains the first question. We are given an integer array NUMS and we have to exactly remove one prefix from this array such that the remaining array is strictly increasing. And we also need to ensure that the length of the removed prefix is minimum possible. And this is the general definition of strictly increasing array if each element is strictly greater than its previous one. I'll go to one of the test case. So the first test case, they have removed the prefix 1 minus 1, 2, 3. After removing this prefix, we will be left with an array 3, 4, 5. And here we can say that 3, 4, 5 is strictly increasing. So coming to the explanation, here we are given an array and we have to remove the minimum prefix. So this is equivalent to as the prefix removed is of minimum possible length, we want the suffix to have max possible length. So basically, I want to find the max uh, possible suffix that is strictly increasing. So this can be pre-computed as follows. Like for example, I will start iterating from the last element of the array, that is at index n plus 1. And uh, I will keep on checking. Like, for example, if I am at index n minus 2, I'll check if the current element is strictly less than its next element. So basically, I start coming from I equal to n minus 2 to 0. I'm taking 0 indexed here. And what I'll check is if a of I is strictly less than a of I plus 1. If this condition is satisfied, I will continue to go backwards. Like for example, if I get that a of n minus 2 is strictly less than a of n minus 1, I'll go backwards and check with a of and check if a of n minus 3 is strictly less than n minus 2. Likewise, I'll go till I encounter a I such that a of I is such that this condition is not satisfied. This is not satisfied. So basically, if I go back till there, I'll be resulting with the maximum possible length of suffix. I guess this will be better if I explain with the code. Here initially, we want the minimum prefix length. So the maximum possible length of prefix is n minus 1. So I have initialized the answer with n minus 1 because if there is so one element, one element case, like if I remove the prefix of size n minus 1, then I'll be resulting an array which has only one element, and one element is always strictly increasing. So maximum possible value of answer is n minus 1. And as discussed before, I'll start iterating from I equal to n minus 2 to 0. And what I'll check is if this condition is strictly increasing condition is satisfied. If the condition is satisfied, I will update the answer to I. So basically, if the condition is satisfied at index I, then the prefix length will be equal to I. I'll explain here. So for example, let the index be 1, 2, 3, 4, 5. So if we found out that suffix till index I equal to 3 is strictly increasing, then the length of prefix will be 3, right? So generalizing this, if at an index I, the suffix till index I is strictly increasing, the length of the prefix will be equal to I. So that's what I did. So if the value is satisfying at index I, the length of prefix will be I. And if at any index this is not getting satisfied, then I'll simply break it. And finally, I am returning the answer. Here, as I am iterating from I equal to n minus 1 to 0, my prefix length keeps on decreasing until I get a case where this condition is not satisfied. So at the end, when I break the for loop, I'll be getting the minimum possible prefix length, and that's all. Now coming to the second question, we are given an integer array nums and an integer k. We have to rotate only the non-negative elements of the array to left by k positions in a cyclic manner. Okay, and all the negative elements must stay in their original positions and they should not move. After rotation, we have to place the non-negative elements back in the array in the new order, filling only the positions that originally contain non-negative values and skipping all the negative positions. And what we have to do is we have to return the resulting array. Coming to this, our target is only non-negative numbers, right? So its value must be greater than or equal to 0. And what they mean by rotate k positions to left is that, let's suppose if I want to rotate this array 2 positions to left, k equal to 2. And let's imagine I'm trying to rotate, or in this case, let's imagine all are non-negative. So k equal to 2 means 2 to left. A4 will go to here, A3 will go to here, A2 will go to A1, and uh, like after A1, it will go to position of A4, and A1 will go to position of A3. So basically, my array will be A4, A3, A2, A1. So from this, we can see if I want to rotate an index I, k positions to left, the element AI will go to the position I minus k. And obviously, we have to take the modulo size of the array because this value can also be negative. So basically, I'm taking modulo with the size of the array. Okay. So this is the key observation. What I have to do is for every index I am taking the AI to position I minus k. And in order to handle the negative one, like if I minus k is negative, even if I take modulo with size, then my resulting answer will be negative. So what I'll do is I'll initially do this modulo size, then I'll again add the size of the array and again take the modulo size. In this way, for example, if I am at index 0 and I want to move 2 positions to left, what will happen is 0 minus 2, that will be equal to minus 2. Okay, here I'll be getting minus 2. Then what I'll do is minus 2 plus 4 modulo 4. This is the size, modulo size. So I'll be getting the index 2 again. So that's what happens when k equal to 2. Index 0 will initially go to one step and two steps. The element at index 0 will go to index 2, and that's all. Now, next step is that this is for the case where we are trying to rotate an entire array. We can simply do this. So, in the main question, what we can do is we can simply like extract the index of non-negative elements and then apply the rotation. Uh, I'll extract the indices into an array. Let this be some array A. And what I'll do here is I'll add the rotation. What rotation does is move A of I to index I plus sorry I minus k plus size I minus k modulo size plus size modulo size. Basically, I am moving for every I am moving it k steps backwards. Now coming to the code of the second question. So initially I have made a copy of the input array and I have also created a vector index. This is to store the indices of all the non-negative numbers. So what I am doing here is if the value of the current element is greater than or equal to 0, then I'll push the index into the array. Okay. Now if the index is empty, like if there are no non-negative numbers, then I'll simply return the initial array as it is. Like there are nothing to rotate, so I can simply return the initial array. So next what I'm doing is I'm initially calculating the size of or basically the number of non-negative numbers. And after that, for every index j, what I am calculating is current equal to j minus k. I'm taking it k steps backwards. Then I'm applying modulo by size of the index array. Then, in order to handle the negative case, I'm adding with size and I'm again taking the modulo. And what is happening here is index of like basically uh, what we want to do is we want to move the element at we want to move element at index of j to index of current, right? So in the new array, what I am doing is at index of current at this place, I am equating it to the value that is present at this index of j. So basically, I am only iterating over non-negative integers in the array, in the initial input array, and I am moving all of them k steps backwards. And finally, I am returning the array, which I have modified. Here we can note that only the non-negative integers indices are changed in this for loop, and the one that are positive are untouched. So that will be satisfied. Okay. Now coming to the next question. We are given an integer n and an undirected tree with n nodes, number from 0 to n minus 1. Okay. And the tree is represented by 2D array of edges of length n minus 1, where basically edge represents the two nodes which it connects. An undirected edge between node U and V. Also, we are given three distinct target nodes X, Y, Z, and for every node U, let dx be distance of U from node X and dy be distance of U from Y. Same dz will be the distance from U to Z. Now, the node U is called special if three distances form a Pythagorean triplet. And we have to return an integer denoting the number of special nodes in the tree. So basically, Pythagorean triplet is any three integers a, b, c, which when sorted in ascending order satisfy the condition a square plus b square equal to c square. And the distance between two nodes in a tree is number of edges on the unique part between them. And that is the question. So coming to the explanation, if we are given three nodes x, y, z, and for every u, dx equal to distance from x to u, dy equal to distance from y to u, and dz equal to distance from z to u. So here, uh, so basically this is a standard question. Like if we are given a node x and we need to find distances from all other nodes to x. We can do this using a breadth first BFS. Okay. So what we do in BFS is we root the tree at the node x, and what we do is we travel the tree level by level, and at every level, so initially the depth equal to 0. So every node at this depth will be at a distance 0, and here depth equal to 1. Every node at this depth will be at a distance equal to 1. Similarly, every node at this depth will be at a distance equal to 2, and this one will be distance equal to 3. And that's all. So for every node x comma y comma z, we will do one BFS each, and we calculate dx comma dy comma dz. After calculating these three, what we'll check is for basically it's best if I maintain a vector like a vector of dx of size n, dy of size n, and dz of size n basically, and dx of I denotes the distance from x to I. And after that, what we have to check for every I is the first, let the dx, dy, dz values be ABC here. A equal to dx. No need for another variable. What I want to do is I can simply explain like this: dxi, dyi, and dzi. I will sort these three values, and after sorting them, let them be A, B, C in sorted order such that A less than or equal to B less than or equal to C. Then I'll check the condition. A square plus B square equal to C square. If this is satisfied, I'll increment the count. And I'll do this for every I from 0 to n minus 1. That's all. Now coming to the code. So here initially I am like we are given in the format of edges, right? So I am pushing it in a adjacency list. And after that I am creating three vectors dx, dy, dz of size n, and I have made a lambda function here The main advantage of lambda function is that if I create a function outside this function, create another function, then I have to pass all the values. Like for example, I'm using the array G adjacency list G here, right? So I have to pass the adjacency list and all other variables. So if I create a lambda function, I can simply write as it is, and there is no need to pass all the other functions which I have used above, all the other variables which I have used above this function. So what this function BFS does is that it takes the index x, and it finds it calculates the distance of all other vertices from the current vertex x, and that will be populated in this vector. So the code is as follows. Initially, I have a visited array, and initially I am pushing the first index in the queue, that is the node x, and after that, while queue is empty, I am going depth-wise here. Uh, Like for example, if the current size of the queue is n, I'll iterate through all the n elements in the depth, and I'll update the value. Like basically, I'll update the distance of the current node I am in to the value depth. And after every time I complete a depth, complete iterating a depth, I will increment the depth counter. So what I'm doing is I'm calling the BFS function three times. What will happen is if I pass y, the distances of all nodes from y will be populated in vector dy. And if I pass z, the distances from all nodes in the tree will be populated in the vector dz. Okay. Now after that, this part is simple. I have initialized a count variable with 0, and after that, I have pushed the squares of all the distances in another vector. Main intention is to sort them. So squares of dx square into into one long because this can overflow as the value of x can be up to 1e5, and 1e5 into 1e5 will be 1e10, and this can overflow if it is an int. So I am multiplying it with a long. And similarly, dx square, dy square, dz square. I am initializing a vector with these values, and I'll sort this vector. After sorting it, what I'll check is, I'll check if the maximum value equal to sum of the smaller two values. Basically, I'll check if c square equal to a square plus b square. If this condition is satisfied, I will increment the count. And finally, I'll return the count. And that's all. Coming to the fourth question, we are given two positive integers n and k, and we have to return an integer denoting the nth smallest positive integer that has exactly k ones in its binary representation. And it is guaranteed that answer is strictly less than 2 power 50. Like for example, with with n equal to 4 and k equal to 2, we can see that the four smallest positive integers that have exactly k equal to 2 ones in their binary representation are 3, 5, 6, and 9. 3 has only two ones, 5 has also two ones, and 6 and 9. As we are asked about the uh, fourth smallest, our answer will be 9. Similarly, for n equal to 3, k equal to 1, the three smallest positive integers that have k equal to 1 are 1, 2, and 4. 2 has only one, and 4 has also only one set bit in its binary representation. So as they have asked n equal to 3, our answer will be 4. Here, the fourth smallest will be obviously 8. 8 has 1, 0, 0, 0 in binary representation, and so on. So, okay, coming to the explanation of this question. So basically, the first observation I have made is, what if I said, like, I have exactly k ones, right? So I initially checked if I set the MSB at location, let this location be current. Like suppose let the size of the number in binary representation be current, and or any variable. Current doesn't sound that well. So let the size of this be x, in size of the number be x, and here what I am fixing is that I am fixing that the xth bit will be 1. Okay, so if my xth bit is 1, I'll be having x minus k zeros, right? Because out of x bit, I must have exactly k ones. So I have x minus k zeros. X minus k zeros. Here the remaining bits are x minus 1, right? Out of remaining x minus 1 bits, x minus k of them are 0. So basically, the number of possible numbers which have the xth bit as 1 are number of possible numbers which have MSB at x are, out of x minus 1 places, I must have x minus k zeros, right? So it will be x minus 1 c x minus k. Okay, these are the number of ways. So what I'll do is, if my if in the question I am given uh, any k value, like I must have exactly k ones. So the possible positions for MSB will be k, k plus 1, k plus 2. It can be no less than k, right? Because I should have k ones, so my MSB will be no less than k. So it can be k, k plus 1, k plus 2, so on. So what I'll do is, if my MSB is at k, I'll find the number of ways. If this number of ways is less than n, then my MSB will be uh, after k only, right? So basically, if my MSB, let this value be equal to ways, for every location, I'll check I'll check the number of ways, like number of possible numbers if my MSB is at k. Let that value be answer. If this number of ways of k is less than n, then my MSB will be at k plus 1. Next, what I'll check if number of ways of k and plus k plus 1, sum of both of these is less than n. If sum of both of these is also less than n, then my answer will be, MSB will be at k plus 2, right? So in that way, I'll keep on checking. I'll be getting an index y such that the number of ways will be greater than n. So in this case, or at y, the summation of number of ways is greater than n, right? So let x be the index where summation of number of ways is less than or equal to x. What this denotes is that my MSP is at x. So after after getting the fact that my MSP is at x, what I'll do is the value of MSP, if it is at a position x, is simply 2 per x minus 1, because I'm taking this as position 1, 2, 3, and here 2 power 0, 2 power 1, 2 square, so on, right? So if it is at a position x, the value will be 2 power x minus 1. So 2 power x minus 1 plus, what I can do here is after fixing an MSB, I'll uh, add its contribution, and then I'll recursively calculate the next MSB in the same manner. Like recursively, let this by initial function that calculates the MSB. So what will happen here is n minus summation of ways, because these many numbers have already used by if I am fixing this as MSB. So my remaining will be these many ways, and then as I have already fixed 1 1 here, I'll be left with k minus 1 ones. So in this way, I have created a recursive formula where I keep on calculating the MSBs, and that will be added to the answer one by one. And finally, I'll return this value. I'll explain with the code, I guess it will be fine. And also in this, for calculating the MSBs, for calculating the number of ways, we need NCR, right? So, and here in question, it's mentioned that the answer will be strictly less than 2 per 50. So basically what we can do is we can pre-compute NCRs for all n less than or equal to 50. Here this is the formula, NCR equal to NCR n NCR equal to NC n minus 1 R minus 1 plus NC n minus 1 R. This can be used for pre-computations of NCR, and after pre-computing all the values, I'm jumping into the main logic. Here, what I am doing is basically current be the last position. Like the last one position can be no less than k, right? Initially, we have discussed that here. The one position should start from k. The MSB position should start from k. Okay. So let the current variable store the current MSB position, and number of zeros will be current length minus k. Okay. And here the number of ways are NCR, current minus 1 places are there, and in that many places I have to place Z zeros. So number of ways will be as follows. If answer plus number of ways is greater than n, then I'll break it. Okay. Else, what I'll do is I'll simply add the number of ways to the answer, and I am incrementing the current pointers. And if in the special case where answer plus number of ways is equal to n, like exactly answer plus number of ways are satisfied, what I am doing here is that when the answer plus number of ways equal to n case, what is happening here is that this will be the highest possible number with MSB at current index. So the highest possible number containing k ones with MSB at current index will be all the k ones will be after the current index and followed by all zeros. And we can greedily see that this is the maximum possible number. So basically, if number answer plus number of ways is equal to n, I want the maximum possible number at current index. So what I am doing is for int I equal to current, I am simply adding I minus 1, like right shifting it to I minus 1. Basically, this is 2 power I minus 1, and I am keep on adding it till I get k1 for all the k1s, and I'll return the sum. If the number of ways equal to n, then this recursive function will end here itself and it will return this sum value. And here, in the case where uh, we get the MSB, we get that MSB is at the position current. What I am doing is, here I am adding 2 power current minus 1 plus 2 power current minus 1 is the current contribution of MSB plus what is there is these are the remaining number of ways. Total number of ways are n, and answer is the number of ways I have used till here, taking basically taking the summation for all k to current value for all possible k values. I'll show it here. Here the number of ways is summation. This is the summation what I was referring to. Number of ways to have MSB at k, number of ways to have MSB at k plus 1, so on till the maximum possible one that satisfies this condition. And after taking all summation of all of those, the remaining number of ways are n minus summation of all the ways. And here I am passing the remaining number of ways. And as I have already used the one here, here I am passing k minus 1 to the recursive function plus I'll recurse it to remaining comma k minus 1. And that's all. After passing this recursive function, we will get the desired answer. Recursively, what this is doing is this keeps on finding the next MSP, which I have to put, and I'll add it to answer. And also here, what I'm doing is I am pre-computing the NCR values only once per solution. Basically, in the constructor of the solution class, I have pre-computed the NCR values from all the values 0 to 51. Just for safety, I have calculated till 51. To 0 to 50 will suffice, I guess, for this question. And that's all. This function returns the value NCR in O of 1. So total time complexity will be, let the number of bits be B. This will go no longer than O of B. So per recursion, what will happen is, let the bits be B. This while loop will run at max the number of bits, and every time this will be called of we are fixing one bit at a time, right? So this recursive function will be called at most k times. So the time complexity of this solution will be k into number of bits, number of bits in n. And that's all. Thank you.